Hello. This video presents the conditions of all three problems of the 16th International Physics Olympiad, which took place in 1985 in Yugoslavia. 16th International Physics Olympiad 1985 IPHO. I offer private tutoring for Physics Olympiad preparation. I currently have openings. There is a discount for group classes. Message me if interested. My email is fred1996@hotmail.com. My Skype name is Eduard F. 1996. Problem 1. Antenna array. A young radio amateur maintains a radio link with two girls living in two towns. He positions an aerial array such that when the girl living in town A receives a maximum signal, the girl living in town B receives no signal and vice versa. The array is built from two vertical rod aerials transmitting with equal intensities uniformly in all directions in the horizontal plane. Question A. Find the parameters of the array, that is the distance between the rods, its orientation and the phase shift between the electrical signals supplied to the rods, such that the distance between the rods is minimum. Question B. Find the numerical solution if the boy has a radio station transmitting at 27 MHz and builds up the aerial array at Port Oros. Using the map he has found that the angles between the north and the direction of A, Koper, and of B, small town of Buj in Istria, are 72 degrees and 157 degrees, respectively. 16th International Physics Olympiad 1985 IPHO. I offer private tutoring for Physics Olympiad preparation. I currently have openings. There is a discount for group classes. Message me if interested. My email is fred1996@hotmail.com. My Skype name is Eduard F. 1996. Problem 2. Hall effect. In a long bar having the shape of a rectangular parallelepiped with sides A, B, and C, A much greater than B much greater than C, made from the semiconductor indium antimonide flows a current I parallel to the edge A. The bar is in an external magnetic field B which is parallel to the edge C. The magnetic field produced by the current I can be neglected. The current carriers are electrons. The average velocity of electrons in a semiconductor in the presence of an electric field only is V equals mu E, where mu is called mobility. If the magnetic field is also present, the electric field is no longer parallel to the current. This phenomenon is known as the Hall effect. Question A. Determine what the magnitude and the direction of the electric field in the bar is, to yield the current described above. Question B. Calculate the difference of the electric potential between the opposite points on the surfaces of the bar in the direction of the edge B. Question C. Find the analytic expression for the DC component of the electric potential difference in case B, if the current and the magnetic field are alternating. AC, I equals I0 sine omega t and B equals B0 sine omega t plus delta. Question D. Design and explain an electric circuit which would make possible, by exploiting the result C, to measure the power consumption of an electric apparatus connected with the AC network. Data. The electron mobility in indium antimonide is 7.8 square meters T over Vs. The electron concentration in indium antimonide is 2.5 by 10 power 22 over cubic meters. I equals 1.0 ampere, B equals 0.10 Tesla, B equals 1.0 centimeters, C equals 1.0 millimeters. Charge of electron E0 equals negative 1.6 by 10 power negative 18 Coulomb. 16th International Physics Olympiad 1985 IPHO. I offer private tutoring for Physics Olympiad preparation. I currently have openings. There is a discount for group classes. Message me if interested. My email is fred1996@hotmail.com. My Skype name is Eduard F. 1996. Problem 3. Escaping the solar system. In a space research project, two schemes of launching a space probe out of the solar system are discussed. The first scheme, I, is to launch the probe with a velocity large enough to escape from the solar system directly. According to the second one, the probe is to approach one of the outer planets, and with its help change its direction of motion and reach the velocity necessary to escape from the solar system. Assume that the probe moves under the gravitational field of only the Sun or the planet, depending on whichever field is stronger at that point. Question A. Determine the minimum velocity and its direction relative to the Earth's motion that should be given to the probe on launching according to scheme I. Question B. Suppose that the probe has been launched in the direction determined in A, but with another velocity. Determine the velocity of the probe when it crosses the orbit of Mars, i.e., its parallel and perpendicular components with respect to this orbit. Mars is not near the point of crossing when crossing occurs. Question C. Let the probe enter the gravitational field of Mars. Find the minimum launching velocity from the Earth necessary for the probe to escape from the solar system. Hint: from the result A, you know the optimal magnitude and the direction of the velocity of the probe that is necessary to escape from the solar system after leaving the gravitational field of Mars. You do not have to worry about the precise position of Mars during the encounter. Find the relation between this velocity and the velocity components before the probe enters the gravitational field of Mars, i.e., the components you determined in B. What about the conservation of energy of the probe? Question D. Estimate the maximum possible fractional saving of energy in scheme 2 with respect to scheme I. Notes: assume that all the planets revolve round the Sun in circles, in the same direction and in the same plane. Neglect the air resistance, the rotation of the Earth around its axis as well as the energy used in escaping from the Earth's gravitational field. Data: velocity of the Earth round the Sun is 30 km/s, and the ratio of the distances of the Earth and Mars from the Sun is 2/3.